Okay, awesome. Yeah, so this is the overview of what we're covering today. We're going to talk about some of the software architectures that generally kind of govern software development. And then we're going to kind of talk about middleware. So that's how we're able to abstract that to a distributed system. And then we're going to talk about some common distributed architectures. And then we're going to lead into the slide. Okay, there we go. Okay, so yeah, let's talk a little bit about what architecture actually is in the context of software development. Uh, so Yep. So yeah, basically there are three main parts. There are components, interfaces, and connectors. So a component is essentially like a single self-contained piece of code or some sort of entity. And we're going to talk about the different architectures, so that'll make a little more sense. But basically, it provides some sort of functionality. The way that components can interact is through their interfaces. So that visually, you can kind of think about it as like two pipes, and they have some sort of way to connect to each other, right? In this case, it's like that pipe. And then connectors are ways to connect two different components. It's a physical kind of medium, I guess, with which the components are connected. So if you have like two nodes, they have to connect over a net, right? So that would be the connector methods. Any questions on those three kind of high-level overview of like architecture? Okay, awesome. So then I'll quickly introduce the four architectural styles that we'll be covering. So there's a layered approach, object-based, resource-based, and event-based. We're going to go into them in detail in a second. Yep. And oh, sorry. And then one last thing here. I'll just make sure that you guys focus on the interfaces between the components, because that's really what's going to distinguish between these four architectural styles when we go through. Okay, so let's talk about a layer-based approach. So this is very, very common. If, for example, if you go to a site like Netflix, what you'll probably see is some sort of front end like that, right? And then you click on the movie that you want to watch. And what's really happening under the hood is when you click on that, it's sending some sort of request to Netflix's server saying, hey, this is the movie that I want. These are the authentication details. Like send me the byte stream or whatever that actually contains the movie. So it executes some sort of code on Netflix's side, and then they have some way to persistently, securely, and efficiently store the actual movie in some sort of database. So their server will query the database, get the data, and then kind of feed it back up through the layers to the front end so that you can actually watch it. So yeah, what we'll see is that there are kind of three structures normally in this approach. There's like the user interface, the front end. There's an application programming interface, API, I guess is generally what you'll hear. And then there's the database level at the bottom. Okay, so yeah, oh, sorry. And then some common protocols that you'll see for communicating between the layers are TCP and UDP. What you'll note is that generally you communicate directly to adjacent layers. So like you won't go from the front end directly to the database. You will go from the database directly to the front end. And you could theoretically have like other layers as well. Maybe if you need to do authentication or something with some third party, depending on the system, it can be designed. But yeah, any questions on the layer-based approach, sir? Okay, cool. So then we can talk about an object-based architecture. So this is something along the lines of what we did at, I believe it was our GM. So the idea is that we have separate nodes or separate kind of, I guess, processes running on those nodes that represent individual components, which is a kind of like a theoretical idea that has some sort of functionality. So here I have the diagram that we showed off here in GM, where we had some sort of calculator component, I guess, that was running on a single node. And then we had our front end that was displaying the actual calculations. So what we can see is that on this node here, our website basically calls this add function, and then the add function kind of goes and calls the calculator node, does the addition, and then feeds it back so it can be rendered on the website. So in our case, each of those nodes are separate computers, right? They're communicating over the network. Okay. So yeah, the key thing here is that this is very analogous to object-oriented programming on like a single machine, right? So those familiar, basically you create classes, and then you can create objects from those classes, and then you can have those interact to do whatever you need to do in your program. Yeah, and generally this is performed with RPC, just like we talked about during GM, and just like you can see in this diagram. And then some of the main advantages here are that you have encapsulation of functionality. So for example, like normally we would just add with the plus sign, right? But maybe we need to change add to do something else. Well, for example, instead of add, we want to have like call a magic like math function. So maybe on even number of days it adds and odd number of days it subtracts, right? What we can do is the client doesn't even need to know about what's happening. We can make all the modifications on the server side. So the functionality is effectively encapsulated into the server name. And then we can also make sure that our client, basically each node is resilient to change, meaning if we make those changes to the server, the client still functions properly. If we make changes to the client, the server still functions properly. Okay, any questions on this object-based approach? Okay, cool. Then we will move on to a resource-based approach. So here I have a bunch of files. Generally, like a very common example is just like a blob storage kind of like cloud service. So what we'll see is that basically we have a single standard interface for every entity in our distributed system. So unlike the object-based approach, where each like type of object, each I guess class, if you're thinking of it in like a traditional sense, has its own interface, like member variables, that kind of thing. Here, everything has the same operations that can be performed on it. So yeah, generally what you'll see is that resources will have some sort of permissions associated with them, which is a way you can kind of specify granularity to those resources. And then each resources can interact with each other through that common interface. So in the case of like S3, which is an Amazon service that basically allows you to upload files of any type, I think they have like a standard put, read, write, delete, just like the kind of common functionality that you'd need for some sort of cloud storage service. And basically you can interact with objects in that way, either through the command line or by clicking on them in the browser. Yeah, commonly what you'll see is that it follows this REST protocol here, which stands for representational state transfer. And that's just basically a set of guidelines for following those kind of predefined like network calls, I guess. I'm not sure what the terminology would be. So basically like that put request, get request to each back. So yeah, what do you guys think are some of the advantages of going with this approach versus the other two approaches that we talked about earlier? And disadvantages. Why might we want to have like what is this? What are some of the limitations of this approach? Well, one thing with this approach, right, keep in mind, is that you have the single standard interface. So if we think about like Google Drive, for example, or some sort of cloud service where you can store files, obviously there's not a whole lot of like customizable functionality there, right? So if we go with a resource-based architecture, it will perform well for a single purpose, but it's not as kind of highly adaptable as like an object-based approach would be, right? Because, like for example, if you're thinking about object-oriented programming locally on your own computer, you can effectively do whatever you want. So yeah, this approach is not as flexible, but generally because of that rigidity, it's more resilient to handle the specific use cases that you need to address. Does that make sense? Yeah, good. So this generally is just a single layer for this. This kind of architecture, I guess.
Not really more of like a software architecture rather than the actual layout of the servers. So like in a resource-based architecture, it's basically defining like the front end interface you would use to interact with it. It would say like it would basically specify that if you have like backend resources and the way you access them is by accessing or modifying those resources. A contrast to that would be like the RPCs where you send in data and you ask the server to perform some sort of computation, right? That would be the alternative to resource-based architecture. And it also doing the computation approach is also something that's like not very suited for like a resource-based architecture. Since you're like essentially like virtualizing your backend resources rather than and it's mainly used in like web dev applications instead of like something like HPC, which is using a completely different interface for that.
talking more about this architecture that is similar to Dropbox or
Yeah, essentially. Yeah, like,
Yeah, this is supposed to be very lightweight. So they're not used for heavy computations. I think if you're looking at like a ubiquitous computing scenario, for example, something like a home network, we have a like thermostat, fridge, whatever. This might be a better idea because you want like a constant interface between them. But and I think an object like based approach would also make sense.
the rest is not state. You don't have any mainstream data between each call. For each you basically ask for resources, a couple parameters, and it will just return it and forget that you even asked in the first place.
Cool. Yeah. Any other questions here on the previous ones? Okay, cool. So then we will move on to the event-based architectures. So yeah, basically what you need to know here is that like in the previous based architectures, everything was what's known as tightly coupled, meaning for example, with the Netflix example, right? If the server goes offline, you can't everything is broken permanently until the server comes back on. So in some cases, or whatever use case we're trying to solve might be amenable to like a what's known as a loosely coupled design. So essentially, what might be happening here is that if the server goes offline, we can send a request and let that request sit until the server comes back online, and then the server will automatically handle that request. So for example, if I need to send an email, but all the servers are offline right now, I can send that email, it'll be queued somewhere, and then once the servers come back online, the email will actually be sent out. So this is what's known as an event-based architecture because we're effectively creating an event, and then the event is processed. So yeah, a very common kind of approach to this, going with this architecture, is what's known as a publisher-subscriber model, or pub sub, sometimes it's called. So essentially, this is what's known as temporally decoupled, but referentially coupled. Effectively, what that means is that we are there's a reference between the publisher and the subscriber, right? They're directly tied together. The subscriber is basically saying, hey, whenever you publish stuff, the subscriber wants to pull it in. But temporally, they're decoupled because if there's some sort of problem with sending the data right now, we can wait until the connection is stable and then send the data later, right? So temporally, it can kind of change over time. Does that make sense? Cool. Okay, and then another approach is what's known as the event model. So this is temporally coupled, but referentially decoupled. So the idea here is that we have some sort of source that's basically sending out events, effectively like shouting out to the world, and then anyone that wants to listen in can choose to do so. So that's why it's temporally coupled because the events are in a fixed point in time, but anybody can listen in if they want to. So like there's no referential kind of relationship between a publisher and a subscriber in this case. Yeah, so let's kind of try to think through some of the advantages of these event-based architectures versus the other approaches. When might these be applicable? Yeah. Yeah, for sure.
really that. Even the server, I guess it gives you a little bit of credibility, I guess, that even though our server is now.
For sure, yeah. I think in any like online business setting where it's critical not to lose requests, right? Maybe you can't process them right now, but generally that first approach is a good idea to kind of build into. Like you generally don't want to have things tightly coupled because if something breaks temporarily, which is very common, then you lose whatever you need to process that, right? But if you have things loosely coupled, you can kind of recover. So yeah, building in ways to recover are what event-based architectures really succeed at, especially in that first one. Yep. Uh, yeah, so I think in the example that I was giving, generally yes. But for example, you could imagine like you send an email, you don't know that it was sent or not, right? So in that case, you wouldn't know unless they tell you. Which in some cases they would, right? They'd probably want to be upfront about it. But Okay, cool. Any other questions or comments on these approaches? Okay, awesome. Then I'm gonna hand it off to Daniel to talk a little bit.
So, let's say you already have a existing legacy distributed system. You know, let's say you want to integrate new features into that. Well, as you know, this is a problem all too common in the software space, where you have every single year you have like a new random front-end React framework or something, always new libraries and things like that. So, with our old code base, it's very big, right? There's like like thousands or even millions of lines of code if you take into account all of the components. And it's really hard to make fundamental changes to it without having to rewrite the entire thing from scratch. And you know, as we can see, the preferred interface styles to interact with these systems are always changing. So now we primarily use HTTP based requests like get, post, put, delete to interact with the backend API. Before, you know, there was something called the SOAP standard. You primarily use XML to encode your requests. In addition, you know, maybe something you want to use in RPC, or maybe you want to enable all three of these methods to interact with our backend, or maybe we want to, you know, just like implement our own custom interface, right? So the fundamental problem is how do we allow these dead legacy systems to continue to function with these changing standards? And so the solution to this is a wrapper. So if you ever use object-oriented programming, you know, you would know that a wrapper is basically taking a class and basically extending the functionality around the existing class. And something similar is happening here. You're basically having an entire component wrapped around your distributed system in order to interface with the new standard. You can essentially think of it as like a translator between different interface methods. And so from here, we see that our component that processes incoming requests that request is getting pre-processed by our adapter, and then it's getting sent to the actual work, which is going to be like our legacy distributed system. And the result comes back, it gets translated again by our adapter, and then it gets sent back to the client. Okay, so next problem we have to discuss is like where do we actually place these wrappers? Like we could have a ton of different interfaces going on in our distributed system, and you know, in the worst case scenario, we would have to do a wrapper for each one of them. Right, and so the solution to this is to use a message broker. And so from here, we see that we have a message broker which provides a uniform interface. So we would only need to put adapters on these three applications to interact with one end of the message broker, and then those two applications to get a wrapper for this other end of the message broker. And the message broker is message passing between these applications. And so, in the words like before, we might have had to create an adapter from application one to every single other application, and so everything would be like directly connected, which is an n squared number of wrappers. However, now we only have to create one adapter for each one of these connections, which only has to interact with our message broker, which is much less work on our end. Okay, and so the next one that middleware tries to solve is how do we access remote resources very easily and very reliably. So middleware provides an interface that allows you to access remote resources. Now, these applications might have specific restrictions, like how do you invoke the functions with various parameters? You know, what about object replications? How do you handle you know, maintain consistency between them? And then load balancing, right? So how can we optimize our request pipeline at the client side? Now, this is a solution called an interceptor. So an intercept is an interceptor intercepts incoming and outgoing messages from the middleware. This which allows for you to customize the remote object identification and create transparency for both the middleware and the user application. Now, it might seem like I'm kind of like rambling on, like, you know, what's the difference between a message broker? We'll get into that on the next slide. So, here's what an interceptor is. So the reason why we do like this is, let's say, your client application, has this application stub, and, you use, old middleware, before, right? And then let's say this like non-intercepted call will work with your old middleware. However, you switch to another one because you like it more or something. And then so now the interfaces don't really match, right? And then so that's why you would add an interceptor to basically pass the function calls from your client application stub to make it compatible with the middleware, and then make the middleware level interceptor compatible with your operating system. And so instead of having to rewrite your client application calls, you would just have to write it in like a very generic interceptor, which is much easier than like having to rewrite your entire client application. Next. Okay, so now we're gonna go over some common distributed system architectures. So obviously, first we have client server. This is a very basic, the most basic architecture. However, it does not scale very well. We have a client ascendant and the server responds to reply. It's obviously very simple, but there's problems. Yeah, that's what we're going with that. So one of the problems is how we communicate between client and server. So as we went over in the beginning slide, the two common protocols are TCP and UDP. However, these two have different trade-offs. The TCP is much more overhead. However, UDP does not provide the delivery guarantees. In addition, you might want to try your own, networking protocol, like Google created Click, for the internal networking. But that's a problem we had to solve for communication. All right, and obviously, as we said before, connectionless protocol for speed, that's UDP. How do we handle lost or corrupted packets? If TCP provides one. How do we deal with retransmissions? And then we also want some certain operations idempotent, which means that it can be repeated without changing the state of or without making the distributed state inconsistent. So basically, you want everything in the same state. You want to keep the system unified. And there's always that comes with that. Okay. So a more complicated version of the client server architecture is called the multi-tier architecture. So in most applications, the functions that you have to create are not going to be cleanly split into the client and server. And so one example of this is the MVC software architecture, right? We have a model, view, and controller. However, these are three things, right? So, how do we split these evenly between the client and server? You're gonna have to do some ugly splits down the middle. And that's why we have a multi-tier architecture. So basically, you have many different layers. One layer called the next, and then that makes it much easier to split these conceptual tasks between your layers of your system. And so here's kind of an example of this. So basically, this maps to the model view controller that we talked about on the last slide. And so our presentation layer is basically going to be like on front end web page. You might have a little bit of local processing on that. But by and large, whenever you want to make a request to the backend, you'd send it to the application layer, which would be like your API, and that would modify your data layer on the bottom, which is like, if you change your user password, it would have to go from here to here to here. Like, you would never modify the database directly. However, one downside of this is that it does increase latency. So instead of having to wait for your request to go to only one hop to your backend server, you have to wait for two hops and then for it to come back as well, which it doubles your latency essentially. All right. And so, some pros of this is that it's very modular. Like you don't have to do some ugly conceptual splits of like which tasks you want to do split between your client and server if you don't split easily. You can just create as many layers as you want. And it's also much easier to update your code in the future. There's much more modularity between the layers. So that you can easily choose which layer you want to add your functionality to. In addition, it's also simple to deploy. Like the physical server architecture is going to map very closely to like the model architecture. So like your logical model control architecture. However, as we talked about before, you're going to have increased latency because of that extra hop that it takes to access your data plane. In addition, whenever you want to add a new feature, you're going to have to probably have to modify all three layers. Which is going to just add a little bit of development time to that instead of just having to modify the front and the back end. You have like another layer that you have to keep track of. All right. And so, why do you want to split tasks between the client and the server? Well, one reason is for the vertical distribution. We have a hierarchy of our workflow that makes it much easier to split our functionality between the various layers of our architecture. In addition, horizontal distribution means that we can split our workload among multiple servers, creating some parallelism to operate on the input data. Right. And one example of a horizontal scale is our sharded database. Instead of having to store all the data into a single database, you can shard them by doing a modulo on the hash piece. Essentially just like split up all your data to make access much faster. Okay, so another architecture paradigm is peer-to-peer. So from the previous like client server architectures, there was a split in the sort of authority, right? So if I control the servers, I can tell you what to do with your client. So if I make a change, that's all up to me. However, for a peer-to-peer, all of the devices are equal. So the devices that are using the distributed system are also going to be the ones powering the distributed system. And so the term we use called the overlay network, which basically defines the structure of that the nodes have in their communication channels. And there's two types: structured and unstructured. And so here's the overlay network. So when we say network, we typically think of like networking, right? Like your router, your switches, things like that. However, as you can see, our overlay network does not contain any of our networking devices. It's only the end devices that are going to be participating in our peer-to-peer network. And so we see that like the connection from this phone to this computer is going to be present in the overlay network. However, our actual network architecture does not really reflect that, right? There are connections that exist in our network architecture that do not exist in our overlay. Okay. And so here's an example of a structured overlay network. So one common one you'll see is like a binary tree, and another one is like kind of a circular topological ring. For reference, like Cassandra, the Cassandra database by Apache uses the circular thing in their clusters. And off the top of my head, I don't really have an example of like the binary tree, but probably a lot of peer-to-peer networks that use that. And so another issue is like, how do we split our data between the nodes? If it's all peer-to-peer and everyone's equal, it's very hard to come up with a clear structure to this. And so what we need is a well-defined way to partition our data evenly. Now, data sets are very rarely distributed. Like if you look at the search trends, the top like Google, whatever, the top search stop websites are gonna have the vast majority of the internet traffic, while everyone else is gonna be like very few. So like this is something that always has to be a concern, right? Like you have to make sure that just because you're that everything is kind of like evenly randomized. We also need a way to map our data to a node, right? And assuming that we have a partitioned data set, right, we need to have a way for the nodes to look up that data. And so we can use a distributed hash table. We'll get back to that later. Another peer-to-peer architecture is unstructured. So as we know, structured, there's a structure to it. Unstructured is kind of all random. So like you don't have no guarantees of your overlay network. And so we can use mathematical models to pretty much assume that all these connections are random. And then usually first the way that this will happen is that when you try to connect to the distributed system, you'll attach to a well-known node. You'll find more peers by flooding the network, and then you'll update your local list. And then there's going to be updates as well as nodes are added and removed from the network. All right. And then how do we get let's see. Yeah, so like a structured peer-to-peer, we typically would want to use that in like a hybrid model. Like there's no guarantee that, let's say for example, like you're using a node for this group, right? If that goes down, you kind of screwed, right? And you're gonna basically have to find a way to rejoin these two, which is why and you're gonna have to do like a lot of operations just to like cascading all of these, uh, doing a lot of like topology changes every time a node is gonna like leave network. But and it's very unexpected, like the impact of like which node is gonna leave. Just because like like the root node is gonna be more important than like one. And the circular ring topology is like much less impactful. Typically you would want to use like an unstructured peer-to-peer network in cases where like joining the distributed system and like, leaving it are very unpredictable. Okay, so how do we find data in our distributed networks? So
Sure. Yeah. So you go back a slide. Okay. So yeah, let's just kind of take the example of an unstructured peer-to-peer model. So hopefully you didn't see it on the slides or you don't have it in front of you. But does anyone have any ideas? Like let's just say we're at a single node, right? We need to find some sort of data that's somewhere in the net. How could we go at it? Hey guys. Okay. Sure. Yeah. If you basically just kind of like send out like tell all the adjacent nodes like, hey, I'm looking for this, and if you don't have it, like tell all your friends, I guess. So you can but yeah, so flooding is a very common approach. Right, this is basically where we just send a request to all of our neighbors, and then have them send it out, and then kind of have it feed it back. Just using recursion. Yeah, just something to keep in mind though is like if all the nodes are doing this, obviously the network is going to be congested, right? Yeah, generally, a way to kind of deal with that is to add like some sort of max hop count or something for the request, so you're not going out into the whole network. Yeah, and then another approach is to take a random walk. So this is basically very similar to flooding, but you only flood, I guess, particular neighbors, or you just kind of go take one neighbor and then kind of take that down all the way to the end until you find where the yep. Go ahead.
How do you do it?
Mhm. Sure.
Like let's say that max out set to that's 100.
Yeah, so in that case, if it's like a structured network, then it wouldn't make sense to send a request out with like a max hops that's like less than the depth, I guess. Yeah, you're still flooding it.
Somewhere.
structured, structured peer-to-peer network, you're gonna have a well-defined way to distribute data, so you would not have to resort to flooding.
Right, you're right. And you can also see unstructured because they realize that. And the data that you store is gone. But it still exists on that graph. Then how would you
Sure.
do
Yeah. I think that's a challenge that folks would have to deal with, kind of on a case by case basis. I feel like what I would do in that situation is, just make sure that you either have data redundantly stored so that that's not an issue, or you're like, cognizant of that possibility so you can handle it like software wide side, or you can maybe add some sort of, uh, like secondary request that sends out, in like a different manner, maybe like using a random walk, that has a longer kind of hop count or something like that. So you could try to find that in an alternative way. Is there anything else to say for that?
Yeah, I mean, it's another way you could do it. You could do that hybrid approach. Instead of only having unstructured, you also have like maybe you know, like authoritative server. We're not going to get into that with later. Like this is a very major issue, and you're right. Like there's a lot of papers trying to deal with this problem.
Yeah, I think the key is to remember, depending on the problems that you're going to face and like your requirements, you want to choose the architecture that you're using, right? So if you're choosing unstructured, peer-to-peer, then that's something that you almost certainly will encounter. So yeah, I guess it's something to either plan for or like not choose that architecture. Cool. So yeah, I guess we kind of got into this a little bit when we were just talking, but there are some problems with unstructured peer-to-peer models. Specifically, the lookups are non-deterministic, right? Because we're sending out a request, but we don't really know what the data is, and it can kind of go on, and maybe it won't even find it. So, yeah, what might be some ideas to fix this, to try to, I think Daniel kind of talked about this a little bit, and we just talked about it a little bit, but what do you guys think? How can we resolve this ambiguity as to where the data actually is?
But, you know, this is this guy.
Yeah, what would it be then?
Yeah,
Yeah, exactly. So we basically want to add some sense of order to our unstructured architecture. So yeah, a common way to do it is through a hierarchical peer-to-peer model. So something like this. Basically, what you need to know is that there's a notion of a super pair, and then there are weak pairs. So the weak pairs are basically the normal kind of nodes that are joining and leaving, and then the super pairs are nodes that kind of manage their adjacent weak pairs. So essentially, if we want to do some sort of search, we can search through the super pairs, to avoid having to deal with the kind of uncertainty of going through all the weak pairs. Yeah, and then I think something that you want to know, make sure that you've accounted for is there needs to be some sort of association between super pairs, right? So when you're setting up your network, you want to make sure you establish that properly. Maybe you want to have an ability to add or remove super pairs in the future, right? So yeah, you want to make sure you actually associate the super pairs properly. Yeah. Okay. Any questions on how this solves those issues? Yep. Yeah, go ahead. Um, I think in this, it depends on the implementation really, but at least from when I've seen this used, the super pairs are in like a very structured network, so they know who's adjacent to them, and they have some sort of sophisticated way to maybe like a distributed hash table or something to know where the data would be in terms of the adjacent super pairs. But in terms of the weak pairs, they don't actually know where the data is. Yeah, probably more than yeah. Cool. Okay. So I think that wraps up all the stuff that we want, like the content that we want to cover today. Any questions on that before we move on? We have a couple of announcements. Yeah, go ahead. That's okay. Um,
It's like with the VPN, you don't use like a distributed system for that. Like you basically could use like a networking protocol like TCP/IP is like an old one. I don't know what to use these days. Like the posting VPN. Like it's basically just like a single link right between the links. And it's like it basically wraps up your traffic by using that VPN protocol. So that wouldn't really be an application of a distributed peer-to-peer system though. Yeah, but if you're asking like if you use a VPN with like the peer-to-peer system, um, yeah, the VPN might cause some issues due to like networking. Because like you can look into it more, but like for example, BitTorrent hasn't been really work. It hasn't been some issues in the past with like NAT, which is like a very common mapping from like a public IP address to a private IP address network space. There's really actual issues with that. These are obviously probably some issues with VPNs as well. But that's also something that you need to consider when implementing your inline network interactions.
Cool. Okay, so we have a couple quick announcements before we actually jump into the project stuff. So yeah, I think we just want to kind of clarify what our plan is, specifically in regards to like the code samples that we're giving out. So yeah, last week we kind of gave you guys a like downloadable, runnable demo. And yeah, our intention is for the product to be driven by you guys. So ideally, you guys are kind of developing the features yourself. But we understand that kind of it's a lot to take in, right? So basically that first week, the code that we've already given out, you guys can use that as a starter template if you'd like. If you feel really confident, feel free to kind of start from scratch though. And then we're planning to release like weekly runnable demos with some of the functionality that we're kind of suggesting you guys implement every week. But ideally, you guys are kind of implementing those features on your own and then looking at the runnable demo to kind of see, oh yeah, this is another way to implement it, or maybe I missed something or something like that. So yeah, take a look at that if you're stuck, but ideally you're implementing it yourselves. Yeah, and then if you're looking for things to do, right, you're not sure what to do, definitely look at the project spec doc. There's a section under each week that's basically has like the feature suggestions for that week, so the things to implement. So yeah, that's kind of that should be your guiding force if you don't know what to do. Any questions on any of that? Okay, cool. So yeah, and then another thing that we noticed from last time is that folks were more or less collaborating verbally, but like not on the same code base. So yeah, we're strongly recommending folks that groups use GitHub, I guess, to like post their code, some sort of code repository to host their code. So yeah, I listed the steps here with some links to actually do it for creating a GitHub repository and then kind of adding folks to the repository so that they can collaborate. If you have any trouble with that though, ping like Daniel and myself. We can definitely help out. Any questions on that though? Okay. And then just some general advice for the project, specifically for this week. So yeah, like I mentioned before, take a look at this if you're looking for things to add. Specifically this week, what we're trying to get you guys to do, and a little bit next week as well, is to kind of split out the client server like dichotomy that we have into a client and still a server, but now the server will have multiple nodes instead of just a single node. So specifically, we want to have this master node here that can kind of load balance both between the workers, and then the master node also needs to be able to keep track of hey, which worker actually has the file that I'm storing, right? So we need some sort of mapping. We've done it in the runnable demo in the separate node here. Theoretically, you could do it on the same node and then maybe move it out later or something like that. But that's kind of the general approach that we're taking. Any questions on the structure though? Okay. Yeah, we'll like walk around and stuff too, so we'll definitely be available to help. But in terms of actually converting the current code that you guys have into something like that, I've laid out some general steps here on one possible approach to do it. So yeah, feel free to take a look at that while you work. Okay. Any last questions on the project stuff before one last announcement? Okay, cool. Yeah. So you want to take this?
So this is um,
Yeah, we'll just keep an eye out. Winter is when I think winter is when we're going to do our recruitment. So that in mind. Okay, cool. Yeah, so hopefully folks from your group are here. I would just try to kind of group up with them. If anyone does not have a group though, I guess like come and see us and we can kind of help aggregate those people.
If you're like, if you have like no one, people listening to your group, maybe like after this try to like DM them on Discord or something, their description will be on the sheet.
Yep.
Yeah, and we can like discuss like splitting up the work, things like that.
Cool. I'll go ahead and stop recording.